Reality, what we perceive as solid, continuous and independent, might not be as fixed as it seems. Some radical theories suggest that reality only truly exists when observed. Whether through quantum physics, philosophy, or thought experiments, the act of observation appears to play a crucial role in shaping what is real. This script will take you on a journey through these mind-bending ideas, exploring paradoxes and experiments that challenge the very notion of existence. Prepare to question everything you thought you knew about the world, because here, reality itself depends on the watcher. The idea that simply observing something can change its state is one of the most startling revelations in modern science. Known as the observer effect, this concept challenges our basic intuition that the world exists independently of us, waiting quietly to be discovered. Instead, it suggests that the act of observation, whether by a human, a device, or any measuring system, can alter the reality being observed. In everyday life, we see subtle examples of this effect all the time. For instance, when you check the air pressure in a tire, the gauge itself might release a tiny bit of air, slightly changing the pressure you're trying to measure. Or if you peek at a baking cake too often, the oven door's heat escapes, affecting how the cake rises. These small disturbances are familiar to us and feel intuitive. We understand that any measurement inevitably interacts with the system. However, the observer effect becomes much more profound and fundamental in the realm of quantum mechanics, the branch of physics that governs the behavior of the smallest particles, electrons, photons, and other subatomic entities. Unlike classical objects, quantum particles don't have definite positions or states when they're not observed. Instead, they exist in a superposition of all possible states, described mathematically as a wave function that spreads out like a cloud of probabilities. When an observation or measurement is made, this superposition collapses into a single definite outcome. The particle suddenly appears at one position, or takes one state, rather than many simultaneously. But what exactly counts as an observation? Is it a conscious mind witnessing the event? Or is any interaction with a measurement device sufficient to force the collapse? The answer remains one of the biggest mysteries in physics. One of the clearest demonstrations of the observer effect comes from the famous double-slit experiment. Imagine firing tiny particles, like electrons, one at a time toward a screen with two narrow slits. If you do not observe which slit each particle passes through, the electrons behave like waves, creating an interference pattern on the detecting screen, bright and dark fringes, showing where the waves overlap or cancel out. It's as if each electron travels through both slits simultaneously, interfering with itself. But if you try to observe or measure which slit the electron passes through, by placing detectors near the slits, the interference pattern disappears. Instead, the electrons behave like particles, forming two clumps aligned with the slits, as if they had gone through only one or the other. The very act of observation collapses the wave-like behavior into particle-like behavior. Here, observation shapes reality in a fundamental way. This phenomenon forces us to reconsider what observation truly means. Is it the consciousness of a human observer that causes collapse? Or is it any physical interaction capable of extracting information about the particle's state? Many physicists argue that measurement devices themselves perform the collapse, regardless of whether a conscious being looks at the data afterward. Others speculate consciousness has a unique role, linking physics to philosophy and mind in a profound way. The observer effect unsettles the classical assumption that reality exists independently of observation. Instead, it hints that the universe might be inherently participatory, that reality emerges only when it is observed. This idea was famously articulated by physicist John Archibald Wheeler through his concept of the participatory universe, where observers are necessary to bring the universe into being. Philosophers, too, have grappled with the implications of observation on reality. The age-old debate between realism that reality exists independently and idealism that reality depends on perception finds new urgency in light of the observer effect. If the universe's fundamental particles behave differently when watched, then what can we say about the nature of existence itself? Moreover, the observer effect is not limited to the quantum world. In social psychology, the Hawthorne effect describes how individuals modify their behavior when they know they are being observed, demonstrating that observation alters outcomes even in everyday human life. On a cosmic scale, some interpretations of quantum mechanics suggest that the entire universe's state depends on being observed, making the role of the observer central to existence itself. Some physicists have even proposed radical ideas that the universe is a vast information processing system, where observation acts as the input triggering the state of reality. This view aligns with digital physics and information theory, which describe reality as emerging from bits of information shaped by interaction and observation. The implications of the observer effect extend beyond physics into metaphysics and even spirituality. If reality depends on observation, then what is the status of unobserved things? Do mountains exist when no one sees them? Does the moon disappear when we look away? While these questions sound like philosophical riddles, quantum experiments force us to consider them seriously. In practical terms, the observer effect teaches humility in how we approach scientific knowledge. We must acknowledge that our instruments, experiments, and even our minds are part of the system we try to understand. We are not detached observers, but participants in the unfolding story of reality. In this section, we've seen how observation is no longer passive. It actively shapes the very fabric of existence. Especially at the quantum level, the observer effect opens a gateway into a mysterious relationship between consciousness, measurement, and reality, one that will guide our exploration through the next sections of this journey into the nature of being. One of the most puzzling and foundational concepts in quantum mechanics is the idea of superposition, the state where particles exist in multiple possible states simultaneously until measured. This notion flies in the face of everyday experience and classical physics, where objects have definite properties and locations at all times. Yet, experiments consistently show that quantum particles behave in ways that only make sense if they occupy multiple states at once. Superposition means that, before observation, a quantum particle like an electron doesn't simply exist in one place or have a single spin direction. Instead, it exists in a blend, a probability cloud encompassing all possible states. This is not just a limitation of measurement, but a real physical condition, as described by the wave function, a complex mathematical description encoding all potential outcomes. This mystery is best illustrated by the classic double-slit experiment, which we briefly touched on in the observer effect. When electrons are fired one by one through two narrow slits onto a screen, they create an interference pattern typical of waves, something impossible if each electron passed through only one slit as a particle. This implies that each electron passes through both slits simultaneously in a superposed state, interfering with itself. The wave function describes this superposition mathematically, but it also poses a serious question: how can something exist in multiple contradictory states at once? If reality is so fuzzy, when and how does it decide on a definite outcome? The process of wave function collapse, where observation forces the superposition into a single state, remains one of the most debated mysteries. Is the collapse a physical process, or is it an artifact of our limited knowledge? Some interpretations of quantum mechanics treat the wave function as a real entity, while others see it as just a tool for calculating probabilities. Adding to the confusion is the fact that quantum superpositions can involve more than just simple position or spin. Entire atoms, molecules, and even small viruses have been shown to exhibit quantum interference, suggesting that superposition isn't limited to the microscopic world, but could potentially extend to larger, more complex systems. This brings profound philosophical challenges. The classical idea that objects have definite properties independent of observation falls apart at the quantum level. Instead, particles exist in a state of possibilities, and reality remains indefinite until an observation or measurement forces a choice. Many scientists and philosophers have tried to interpret this weirdness. The Copenhagen interpretation, one of the earliest and most popular, accepts wave function collapse as a fundamental process triggered by measurement. It maintains a practical approach, focusing on predictions rather than deep explanations, but it leaves unanswered what constitutes a measurement or an observer. Other interpretations, like many worlds, deny collapse altogether, suggesting that every possible outcome of a quantum event actually happens, branching into separate parallel universes. In this view, superposition never disappears. Instead, reality splits endlessly into different versions. More recently, ideas like decoherence attempt to explain why superpositions seem to collapse in practice. Decoherence proposes that interaction with the environment causes quantum systems to lose their superposed states, appearing classical. Yet decoherence doesn't explain why a particular outcome is realized. It just explains the disappearance of interference patterns. Superposition also raises questions about the role of consciousness in observation. Some propose that a conscious observer's awareness is what causes collapse, making reality dependent on mind. Others reject this, arguing that physical interactions alone suffice to resolve superpositions. Regardless of interpretation, quantum superposition challenges our deepest intuitions about reality. It forces us to accept that, at its core, nature is probabilistic and indeterminate. with outcomes emerging only upon interaction. This mystery extends into technology too. Quantum computing exploits superposition by encoding information in qubits that can be both 0 and 1 simultaneously, promising computational power far beyond classical machines. Yet harnessing and maintaining superposition is notoriously difficult, requiring isolation from environment-induced decoherence. In summary, quantum superposition reveals a reality that is not fixed or definite, but fluid and probabilistic. It shows a universe that, before observation, exists as a cloud of possibilities rather than a solid, definite structure. Understanding this concept is essential for grasping how observation intertwines with existence and sets the stage for the paradoxes and theories that follow in this journey. Among the many thought experiments that highlight the strange implications of quantum mechanics, Schrödinger's cat stands out as one of the most famous and provocative. Proposed in 1935 by Austrian physicist Erwin Schrödinger, the paradox was designed to illustrate the absurdity of applying quantum principles like superposition to everyday objects. Yet it remains central to debates about the nature of reality and observation. Imagine a cat placed inside a sealed box. Inside the box is a radioactive atom, with a 50% chance of decaying within an hour. If it decays, it triggers a mechanism that releases poison, killing the cat. If it does not decay, the cat remains alive. According to quantum theory, until the box is opened and an observation made, the atom exists in a superposition of decayed and undecayed states. By extension, the cat is simultaneously alive and dead, both outcomes existing at once. This idea is deeply unsettling because it conflicts with our everyday experience. In reality, cats are never both alive and dead at the same time. Yet, quantum mechanics suggests that, at the fundamental level, particles do exist in superpositions, so why shouldn't the same apply to larger systems? Schrödinger devised this thought experiment to highlight the tension between quantum theory and classical reality. The paradox raises a crucial question. When does the superposition end and a definite outcome emerge? Is it when a conscious observer opens the box, or does the interaction of particles inside the box cause the collapse? This question touches on the infamous measurement problem, the puzzle of how and why quantum probabilities resolve into specific realities. Schrödinger's cat challenges the notion of an observer-independent reality. If the cat is both alive and dead before observation, does that mean reality is incomplete or indeterminate without a witness? Or is the universe branching into multiple realities where the cat is alive in one and dead in another? This dilemma led to several interpretations. The Copenhagen interpretation suggests the act of measurement causes the wave function to collapse, forcing reality to choose a single state. But what counts as a measurement? Does the cat's own biological processes constitute observation, or is an external conscious observer required? The many worlds interpretation bypasses the collapse problem by positing that both outcomes occur, but in separate, parallel universes. In one universe, the cat lives. In another, it dies. The observer becomes entangled with the outcome, splitting their own reality. While this elegantly solves the paradox mathematically, it introduces the challenge of infinite branching worlds. Others have proposed that decoherence, the loss of quantum coherence due to interaction with the environment, explains why macroscopic objects like cats don't appear in superpositions. According to decoherence theory, the cat rapidly interacts with countless particles around it, forcing the system into a classical state. However, decoherence doesn't specify why one outcome occurs instead of another. It only explains the disappearance of interference. Philosophers and physicists have debated Schrödinger's cat extensively, using it as a focal point to examine the relationship between consciousness and reality. Some argue consciousness is necessary for collapse, giving the mind a fundamental role in shaping the physical world. This idea resonates with idealism, the philosophy that reality depends on perception. Others reject this, emphasizing an objective reality that exists regardless of observation. They point out that quantum experiments show collapse can occur through physical interactions, not requiring a conscious observer. The cat paradox also extends beyond physics into questions about the nature of life and death, existence and potentiality. The idea that something can be both alive and dead simultaneously challenges the boundaries between possibility and actuality. It forces us to confront the limits of language and logic when applied to quantum phenomena. In popular culture, Schrödinger's cat has become a symbol of paradox and uncertainty, often invoked to represent situations where contradictory states coexist. Its influence extends into philosophy, psychology, and even art, inspiring reflections on ambiguity and duality. On a practical level, the thought experiment highlights the difficulties of applying quantum rules to macroscopic objects. While quantum mechanics governs all matter, the effects become less noticeable at large scales due to decoherence and complex interactions. Still, Schrödinger's cat remains a vivid illustration of the puzzles surrounding observation and reality. It invites us to question whether the world exists in a definite state before we look, or if the act of looking itself shapes existence. In the context of this script, the paradox sets the stage for exploring how consciousness, observation, and reality intertwine. It forces us to confront the uncomfortable idea that what we call reality might depend fundamentally on whether it's being observed, pushing us deeper into the mysteries of existence. One of the most fascinating and controversial questions in quantum mechanics is the role of consciousness in the collapse of the wave function. Does the act of conscious observation cause the indefinite possibilities of a quantum system to snap into a single definite reality? This idea challenges both physics and philosophy, and has sparked intense debate since the early days of quantum theory. At the heart of the issue lies the measurement problem. How and why does a quantum system, described by a wave function representing multiple possibilities simultaneously, suddenly reduce to a single outcome when measured? The mathematical formalism of quantum mechanics is clear about what happens during measurement, but it remains silent on what physically causes the wave function to collapse. Some interpretations suggest that the collapse is not a physical process at all, but a reflection of the observer's knowledge updating. Others claim that physical interaction with a measuring device suffices, no consciousness needed. However, a provocative alternative posits that conscious awareness itself plays a crucial role in actualizing reality. This idea was championed by notable figures, such as the physicist Eugene Wigner, who argued that consciousness causes collapse. According to Wigner, the physical world remains in a superposed state until observed by a conscious mind. Until then, all possible states coexist in a nebulous quantum haze. This perspective aligns with certain strands of philosophical idealism, which hold that reality is fundamentally mental or dependent on perception. If consciousness causes collapse, the universe may be incomplete or unreal until it is observed by sentient beings. But how does consciousness achieve this? The mechanism remains unclear and deeply mysterious. Some theories suggest that the act of conscious observation selects one possibility from the quantum superposition, collapsing the wave function and making one outcome real. This introduces an almost magical quality to the mind, elevating it from a passive witness to an active creator of reality. Critics argue that this idea borders on metaphysics rather than science, lacking empirical evidence or testable predictions. They point out that wave function collapse occurs even in situations without any conscious observer present, such as in automatic detectors or interactions with the environment. Nevertheless, experiments like the delayed choice quantum eraser complicate the picture. These experiments show that choices made after a quantum event can influence whether it behaved like a wave or a particle in the past, suggesting a deep entanglement between measurement, observation, and reality that defies classical logic. Moreover, some researchers propose that consciousness itself may be a quantum phenomenon. Theories like the orchestrated objective reduction, OR hypothesis, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggest that quantum processes within brain microtubules could link consciousness and quantum mechanics at a fundamental level. If true, this might explain why consciousness could play a role in wave function collapse. Despite these theories, the scientific community remains divided. Most mainstream physicists favor interpretations that do not assign a fundamental role to consciousness. The decoherence theory, for example, explains collapse-like phenomena through unavoidable interactions with the environment, eliminating the need for a conscious observer. However, the question persists, can consciousness be fully explained by classical physics and biology, or does it transcend to the quantum realm? And if consciousness is essential to reality's formation, what does that imply about existence without conscious observers? The idea that reality depends on conscious observation challenges the classical worldview of an objective, observer-independent universe. It suggests a universe intimately tied to awareness, blurring the boundaries between mind and matter. Philosophically, this view opens questions about the nature of existence, the meaning of observation, and even the role of human beings in the cosmos. Are we passive spectators, or are we co-creators of reality through our conscious experience? Such reflections have profound implications beyond physics, influencing debates in philosophy of mind, metaphysics, and spirituality. Some mystical traditions echo this notion, teaching that consciousness shapes or even creates the world we perceive. In conclusion, the relationship between consciousness and wave function collapse remains one of the most intriguing puzzles of modern science. While no definitive answer exists yet, exploring this connection pushes us to reconsider the nature of reality and our place within it. As we continue through this journey, the mystery of consciousness and its possible role in shaping the observed universe will reappear, inviting deeper reflection. The Wigner's friend thought experiment, proposed by physicist Eugene Wigner in 1961, deepens the mystery of quantum measurement and the role of consciousness in reality. Building on Schrödinger's cat paradox, it explores what happens when two observers, one inside and one outside an isolated system, disagree on the state of a quantum event, raising profound questions about objectivity, consciousness, and the nature of reality. Imagine a scenario. Inside a closed laboratory, Wigner's friend performs a quantum measurement on a system, say detecting the spin of an electron. According to standard quantum mechanics, before measurement, the electron is in a superposition of spin-up and spin-down states. When Wigner's friend observes the outcome, the superposition collapses, and they see a definite result, spin-up or spin-down. From the friend's perspective inside the lab, the measurement is complete, and the system has a definite state. But for Wigner, who is outside the lab and does not know the outcome, the entire lab, including the friend and the electron, is itself in a superposition of friend saw spin-up and friend saw spin-down. Until Wigner observes or measures, he must treat the lab as a quantum system in superposition. This leads to a paradox. The friend experiences a definite reality, but Wigner must treat that same reality as indefinite and superposed. Who is correct? Does the wave function collapse when the friend observes, or only when Wigner observes the friend? The Wigner's friend experiment reveals a tension between subjective experience and objective description. It suggests that quantum states, and thus reality, might depend on the observer's knowledge and perspective, challenging the notion of a single, observer-independent reality. This paradox pushes the boundaries of the measurement problem even further. It forces us to ask, what exactly constitutes an observer? Is consciousness required? Can observers themselves be treated as quantum systems? And if so, can different observers have contradictory accounts of reality simultaneously? Several interpretations attempt to address this. The Copenhagen interpretation tends to place measurement and collapse at the level of conscious observation, but struggles to explain whose consciousness counts when observers observe other observers. The many worlds interpretation offers an elegant solution by suggesting that all outcomes occur, but observers become entangled in branching universes, each experiencing one definite outcome. In this view, there is no contradiction. Both Wigner and his friend exist in superposed but non-interacting branches. More recent developments, like the relational interpretation, propose that quantum states are relative to each observer. In other words, what is definite for Wigner's friend may be indefinite for Wigner. Reality is fundamentally relational, not absolute, depending on who observes what. The Wigner's friend paradox also intersects with the debate over consciousness and collapse. If consciousness causes collapse, then the friend's observation should fix reality. But if Wigner can still treat the lab as a superposition, does Wigner's consciousness have a role in recollapsing reality, or is consciousness insufficient to determine absolute states? Experimental advances have begun to test aspects of these paradoxes, using increasingly complex quantum systems that mimic observers measuring other observers. While not involving actual consciousness, these experiments probe the boundaries of superposition and measurement, shedding light on whether observer-dependent realities exist. Philosophically, the Wigner's friend scenario challenges the idea of an objective, absolute reality. It suggests reality might be observer-dependent at a fundamental level, with no single, universal truth about quantum states. This has wide-ranging implications beyond physics. If realities can differ between observers, even when they are physically connected, what does that say about the nature of truth, knowledge, and perception? Could this idea extend metaphorically to human experience, where different perspectives shape different realities? In the context of the theme, theories that reality only exists if someone's watching, Wigner's friend illustrates that someone watching may not be a simple notion. Different observers might disagree on what is real until they compare notes, and even then, quantum mechanics suggests reality remains stranger than any classical picture. This thought experiment pushes us to reconsider the role of consciousness, measurement, and information in constructing the world we perceive. It hints that reality may be an intricate web of relationships between observers, each bringing their own perspective to the quantum stage. As we move forward, the ideas raised by Wigner's friend will resurface, inviting us to explore interpretations like participatory universe ideas, delayed choice experiments, and relational quantum mechanics, all of which probe the boundaries of observation and existence. The notion of a participatory universe is one of the most profound and philosophically charged ideas in modern physics. Popularized by physicist John Archibald Wheeler in the late 20th century, this concept suggests that the universe doesn't merely exist passively, but requires the participation of observers to bring reality into being. In other words, reality is not complete or fixed until it is observed, making observers active co-creators of the cosmos. Wheeler's participatory universe builds on the quantum measurement problem and the observer effect, but takes them to a cosmic scale. Instead of limiting the observer's role to laboratory experiments or isolated particles, Wheeler argued that the entire universe is shaped by observation, and without observers, the universe's reality remains undefined. This idea arose from Wheeler's engagement with quantum mechanics and cosmology. He was intrigued by the strange implications of quantum experiments that suggested observation collapses superpositions and creates definite states. Extending this to the universe as a whole, he posed the question, does the universe exist independently, or does it come into being through observation? One of Wheeler's famous phrases was, "it from bit," implying that physical reality, it, arises from binary yes or no questions, or bits of information generated by observation. In this view, information and observation are fundamental, more so than traditional matter or energy. The universe is essentially a vast network of informational exchanges that require observers asking questions. This participatory framework challenges the classical idea of a fixed, objective reality. Instead, reality is dynamic and emergent, created in the interplay between the cosmos and the conscious minds observing it. The universe is not a clockwork machine ticking along independently, but a participatory dialogue between what is observed and who observes. Wheeler illustrated this concept through thought experiments such as the delayed choice experiment, which shows that choices made by observers seemingly influence past events, suggesting that the act of observation reaches backward in time to shape reality. The participatory universe implies a feedback loop between observers and the cosmos. The universe produces observers through evolution, and observers in turn help bring the universe into definite existence by observing it. This cyclical relationship means the cosmos and consciousness are intertwined at a fundamental level. This idea has resonances with various philosophical and spiritual traditions, which emphasize the interdependence of consciousness and reality. It aligns with certain strands of idealism and phenomenology, which propose that reality depends on experience and awareness. However, the participatory universe also faces challenges. Critics ask whether the universe can exist before any observers evolved, and how the first observations could bring reality into being if nothing existed to observe. Wheeler addressed this by suggesting a sort of self-excited circuit, where the universe creates observers who then participate in creating the universe's reality in a loop without a clear beginning. This recursive concept pushes the boundaries of scientific explanation and enters the realm of metaphysics. It raises deep questions about causality, temporality, and the nature of existence. Can a universe be both cause and effect of conscious observation simultaneously? Moreover, the participatory universe highlights the role of information in physics. Instead of focusing solely on particles and fields, it frames the universe as an information processing system, where reality emerges from acts of measurement and observation encoded as bits. This informational approach influences contemporary physics and quantum information theory, suggesting that reality's fabric is woven from data and observations rather than physical substance alone. In practical terms, the participatory universe idea influences how we interpret quantum experiments and guides new theoretical frameworks that integrate information, computation, and consciousness. Philosophically, it urges us to reconsider our place in the cosmos, not as passive observers, but as active participants, whose awareness shapes existence itself. This perspective carries profound existential and ethical implications, emphasizing interconnectedness and responsibility. In summary, the participatory universe idea presents a radical vision where reality is not a fixed backdrop, but a living process co-created by observers and the cosmos. It invites us to see observation not as a passive act, but as a powerful creative force that brings the universe into being. As we continue our exploration, this concept will illuminate the intertwined nature of mind, observation, and reality at the heart of quantum mysteries. The delayed choice quantum experiment is one of the most mind-bending illustrations of how observation seemingly shapes reality, even after the fact. Originally proposed by John Archibald Wheeler in the 1970s, this experiment challenges our classical intuition about time, causality, and the nature of measurement, suggesting that choices made in the present can influence the behavior of particles in the past. To understand the delayed choice concept, it helps to revisit the famous double-slit experiment, where particles like photons or electrons create an interference pattern, evidence of wave-like behavior when not observed, but behave like particles when measured at the slits. In Wheeler's delayed choice variation, the experiment is arranged so that the decision to observe which path the particle takes is made after the particle has passed through the slits, but before it reaches the detector. Classically, this seems impossible. How could a choice made after the particle's passage influence what happened earlier? Yet, quantum mechanics predicts and experiments confirm that the particle behaves according to whether or not it will be observed, even if the choice to observe happens after it passed the slit. This phenomenon implies a retrocausal effect, where future actions affect past events. It suggests that reality is not fixed until measured, and measurement outcomes are not merely passively recorded, but actively create the particle's history. The particle's past trajectory becomes undefined or open, until the observation closes the loop. Wheeler illustrated this with a cosmic-scale delayed choice scenario, imagining photons traveling billions of light-years from distant quasars. The decision to observe or not observe their path could be made long after the photons were emitted, implying that the present observer influences how those photons behaved in the distant past. Such experiments force us to rethink the concept of time in quantum physics. Unlike classical physics, where cause precedes effect in a straightforward timeline, quantum mechanics allows for more flexible relationships, where measurement collapses the wave function in ways that defy classical causality. The delayed choice experiments also highlight the crucial role of the observer. They suggest that reality is not a static narrative unfolding independently, but a participatory process, where observation brings events into definitive existence, even rewriting history in a sense. Many interpretations of quantum mechanics grapple with delayed choice effects. The Copenhagen interpretation accepts the collapse as fundamental, but struggles with how the collapse seems to reach back in time. The many worlds interpretation explains the effect by branching timelines where all possibilities occur, but the observer's branch reflects a consistent history. Other interpretations, like relational quantum mechanics, propose that facts are relative to observers, so the particle's past state is only defined once observed, eliminating the paradox of retrocausality. Philosophically, delayed choice experiments raise profound questions about free will, determinism, and the nature of reality. If present choices influence the past, then our actions are intertwined with the fabric of time itself, challenging linear, mechanistic worldviews. In practical terms, these experiments demonstrate the delicate and subtle nature of quantum systems and measurement. They highlight the need for careful interpretation of quantum phenomena, emphasizing that measurement outcomes depend on the entire experimental setup, including choices made after the particles' interaction. Delayed choice quantum experiments also inspire new approaches in quantum information science, where control of quantum states and timing of measurements are key to technologies like quantum computing and cryptography. Despite their strangeness, these experiments are well tested and reproducible, showing that the quantum world defies classical intuition, but follows a consistent set of rules, a quantum logic that challenges how we understand time and reality. In conclusion, the delayed choice quantum experiment reveals a universe where observation shapes not just the present but the past, weaving a reality that is flexible, participatory, and deeply connected to the observer's choices. It opens a door to a worldview where time is not a simple arrow, but a complex interplay between events, measurements, and consciousness, pushing us further into the mysteries of how reality exists only if someone's watching. Relational quantum mechanics (RQM) is a thought-provoking interpretation of quantum theory that reframes the concept of reality itself. Proposed by physicist Carlo Rovelli in the 1990s, RQM suggests that the properties of quantum systems such as position, momentum, or spin are not absolute or objective. Instead, these properties exist only relative to other systems that interact with them, meaning that reality is fundamentally relational. At the heart of this idea is a radical departure from classical physics, where objects are thought to have inherent, observer-independent properties. In contrast, RQM posits that quantum states and values emerge only through interactions or measurements between systems, There is no universal, absolute state of any object. Each observer or system may have its own description of reality. Imagine two observers, Alice and Bob, who each measure the spin of an electron. According to RQM, Alice's measurement results are real relative to Alice, and Bob's results are real relative to Bob. However, these realities may differ, and there is no overarching absolute fact that both must agree on, unless they interact and compare notes. In other words, physical facts depend on the relationship between observer and observed. This relational perspective elegantly resolves some quantum paradoxes that hinge on the idea of absolute states. For example, the Wigner's friend paradox, where an observer inside a lab and an outside observer disagree on the state of a system, fits naturally into RQM. Each observer has a valid relative account of reality that is consistent within their frame, but may differ from others until interaction occurs. RQM challenges the classical notion of a single, objective reality, replacing it with a network of relational facts. This does not mean reality is arbitrary or purely subjective, rather facts exist, but only in relation to other physical systems. Reality is thus contextual, depending on the information exchange between observers and systems. The interpretation also shifts the focus from consciousness to physical interactions. Unlike interpretations that emphasize the observer's mind, RQM treats all physical systems, even inanimate measuring devices, as potential observers. Any interaction that results in a correlation between systems counts as a measurement and generates relative facts. This view is consistent with quantum mechanics formalism, which treats measurement outcomes as correlations between systems. RQM provides a conceptual framework that explains why different observers might have different accounts without contradiction or paradox. Moreover, RQM offers insights into the nature of time and causality. Since facts are relational and contextual, the temporal order of events can vary depending on the observer's frame of reference. This flexibility aligns well with relativistic physics, which rejects absolute simultaneity and embraces observer-dependent timelines. Philosophically, RQM resonates with ideas from phenomenology and process philosophy, which emphasize relationality, context, and interaction as foundational. It also parallels certain interpretations in social sciences and cognitive science, where reality is constructed through relationships and exchanges. RQM's relational ontology invites us to reconsider what it means to say something exists. Instead of independent, self-contained objects, existence becomes a web of interrelations where properties emerge only through interactions. This view aligns with the participatory universe idea, highlighting that observation and interaction are essential for reality's manifestation. Despite its conceptual elegance, RQM faces challenges. Critics question how to reconcile the many different relative realities into a coherent picture of the world. The theory also leaves open how and when observers compare their accounts and establish shared facts, a process that in practice involves communication and classical information. Experimentally, RQM makes the same predictions as standard quantum mechanics, so it is difficult to test directly. However, it provides a philosophically consistent way to understand quantum phenomena without invoking wave function collapse or many worlds branching. In summary, relational quantum mechanics offers a revolutionary lens to view reality, not as an absolute fixed stage, but as a dynamic network of relationships, where facts and properties emerge only through interactions. It challenges us to rethink the meaning of observation, existence, and objectivity, and it deepens the theme that reality depends on the observer, not necessarily a conscious mind but any system in relation. As we continue exploring theories that reality only exists if someone's watching, RQM stands out by emphasizing that watching is fundamentally about interaction and relationship. Reality is not simply out there, it is co-created in the relational dance of the quantum world. At the core of quantum mechanics lies one of its most perplexing and enduring puzzles, the measurement problem. It arises from the fundamental question of how and why the probabilistic, fuzzy quantum world, described by a wave function containing many possible outcomes, gives rise to the definite, concrete reality we experience. Put simply, why does measurement produce a single result instead of leaving systems in multiple states? Quantum systems exist in a superposition of possible states, described mathematically by the wave function. Before measurement, a particle can simultaneously be in multiple positions or spin directions, represented as a combination of all these possibilities. However, when a measurement occurs, the wave function appears to collapse suddenly to one definite outcome. This transition from multiple potential realities to a single actuality is what the measurement problem attempts to explain. The problem is subtle yet profound. The Schrödinger equation, the fundamental equation governing quantum evolution, predicts continuous, smooth changes in the wave function, but measurement seems to introduce a discontinuous probabilistic jump to a single state, defying the usual laws. This duality between smooth evolution and sudden collapse is central to the measurement problem. Another complication is defining what exactly counts as a measurement. Is it an interaction with a macroscopic device, a conscious observer, or something else? Traditional quantum mechanics doesn't specify the boundary between the quantum world and classical measurement apparatus. This ambiguity leads to paradoxes like Schrödinger's cat, where the line between quantum superposition and classical definiteness blurs. Different interpretations of quantum mechanics tackle the measurement problem in varying ways. The Copenhagen interpretation, the earliest and most widely taught, accepts collapse as a fundamental but somewhat mysterious process triggered by measurement. It emphasizes the role of classical measuring devices, but leaves open the exact physical mechanism of collapse. The many worlds interpretation offers a radical solution by rejecting collapse altogether. Instead, all possible outcomes occur in branching, non-communicating parallel worlds, with the observer becoming entangled with each outcome. Measurement doesn't select one reality, but creates a multiverse of realities. While mathematically consistent, this interpretation challenges our intuition about reality's uniqueness. Other approaches include objective collapse theories, which propose that collapse is a physical process caused by factors like gravity or reaching a threshold of complexity, independent of observers. These models aim to provide testable predictions about when and how collapse occurs, bridging quantum and classical worlds. The decoherence program explains how interaction with the environment effectively washes out quantum superpositions, making systems appear classical without invoking collapse. While decoherence solves why we don't observe superpositions at large scales, it doesn't fully solve the measurement problem, as it doesn't explain how a particular outcome is chosen. Philosophically, the measurement problem raises deep questions about reality, objectivity, and the role of observers. If measurement determines reality, is the universe fundamentally indeterminate until observed? Does consciousness play a special role, or is reality independent of measurement, but only appears definite to us due to practical limitations? Practically, the measurement problem influences the development of quantum technologies like quantum computing and quantum cryptography, where controlling measurement and decoherence is vital. Despite decades of study, no consensus exists on the measurement problem's resolution, making it a fertile ground for both scientific research and philosophical inquiry. In the context of theories that reality only exists if someone's watching, the measurement problem highlights the fundamental entanglement between observation and existence. It suggests that what we call reality may depend not just on passive existence, but on active interaction and measurement, challenging classical assumptions and inviting us into the strange, fascinating realm of quantum mystery. In recent decades, a compelling idea has emerged at the crossroads of physics, computer science, and philosophy, that reality is fundamentally information. This perspective suggests that the universe, at its core, is not made of matter or energy alone, but is a vast processing system of information, with physical phenomena arising from informational processes. This shift from material substance to information reshapes how we understand reality and its dependence on observation. The concept of reality as information builds on insights from quantum mechanics and digital physics. Quantum theory reveals that particles behave not as fixed objects, but as probability waves encoding possible states. Meanwhile, advances in computing and information theory show how complex systems can emerge from simple informational rules. Together, these developments suggest that the universe itself may be a giant information processor. Physicist John Archibald Wheeler famously summarized this idea with the phrase, "it from bit." He proposed that every physical entity, every it derives from binary choices, yes or no questions, or bits of information. In this view, particles, forces, and space-time emerge from fundamental acts of measurement or observation, which are themselves acts of acquiring information. If reality is information, then the role of observation becomes central. Measurement is not just recording a pre-existing state, but generating new bits of information that define reality itself. This aligns with the quantum measurement problem, where observation collapses possibilities into a definite outcome, creating new facts. Viewing reality as informational also connects to the idea of the universe as a computational system. Some theories propose that the cosmos operates like a quantum computer, processing information through the interactions of quantum bits, or qubits. These qubits can exist in superpositions, allowing vast parallel computation and giving rise to the complexity we observe. This computational view suggests that the laws of physics are akin to software rules governing the processing of information. Physical phenomena, particles, fields, forces, are emergent patterns in this underlying informational substrate. Space and time themselves may arise from quantum entanglement and information flow, rather than existing as fundamental backdrops. Philosophically, reality, as information, blurs the boundary between observer and observed. Since information requires a receiver and a sender, the act of observation and interaction is integral to existence. The universe becomes a participatory system, where observers and phenomena co-create reality through informational exchanges. This perspective also resonates with ideas in consciousness studies. Some propose that consciousness arises from complex informational processes, suggesting that mind and reality share a common informational basis. This challenges classical materialism and opens new dialogues about the nature of mind, matter, and information. The informational view of reality has practical implications in physics and technology. Quantum information theory, quantum computing, and cryptography exploit the informational nature of quantum states, promising revolutionary advances. Understanding reality as information could unify physics' fundamental forces and shed light on quantum gravity and black hole information paradoxes. However, this view raises challenging questions. If reality is information, what is the nature of the hardware running the cosmic computation? Who or what is the observer that processes information? Does information exist independently, or is it always relative to observers? These questions connect back to the theme that reality only exists if someone is watching. Information cannot exist in a vacuum. It requires interaction and context. Thus, the universe's reality emerges from an ongoing informational exchange between systems and observers, reinforcing the idea of a participatory cosmos. In summary, conceiving reality as information transforms our understanding of existence from a static material world to a dynamic, interactive web of informational processes. Observation is not merely passive, but a creative act generating the bits that build the universe. This conceptual shift offers profound insights into how and why reality depends on observation and challenges us to rethink the very nature of being. The simulation hypothesis is a radical and intriguing idea that proposes our entire reality might be a sophisticated simulation run by an advanced civilization or intelligence. According to this hypothesis, everything we perceive, our universe, ourselves, and all physical phenomena, could be part of an artificial digital construct, much like a highly advanced computer game. This concept challenges the very nature of reality and ties directly into the theme that reality exists only if observed, or in this case, programmed. The hypothesis gained prominence largely through philosopher Nick Bostrom's influential 2003 paper, where he argued that one of the following must be true. 1. Almost all civilizations at our level of development go extinct before developing the capacity to run detailed ancestor simulations. 2. Advanced civilizations have no interest in running such simulations. Or 3. We are almost certainly living in a simulation. If the third is true, our perceived universe is a product of information processing carried out by some higher intelligence. In this framework, what we call reality is essentially data, bits encoded and manipulated by computational processes. The simulation runs algorithms that generate consistent physical laws, space, time, matter, and consciousness within the program. From inside the simulation, we have no direct way to access the base reality or the hardware running the simulation. One way this idea connects to quantum mechanics and observation is through the role of information. Just as digital computers render images and states only when observed or interacted with, the simulated universe might render, or collapse, quantum states when they are observed by simulated observers. This would make observation a fundamental trigger in maintaining the coherence of the simulation, tying back to the idea that reality exists because it is being watched. Some proponents speculate that the peculiarities of quantum mechanics, such as superposition, entanglement, and the measurement problem, might be artifacts of the simulation's computational shortcuts or limitations. Quantum randomness could be the simulation's way of efficiently managing resources by not rendering states until necessary, akin to how video games render only what the player can see. Philosophically, the simulation hypothesis forces us to reconsider notions of existence, consciousness, and free will. If our reality is a simulation, is consciousness simply a byproduct of complex algorithms? Are our choices predetermined by the program's code, or do we have genuine agency within the simulation? Critics argue that the hypothesis is unfalsifiable. There is no empirical test yet to confirm or deny it, making it more philosophical speculation than scientific theory. However, some physicists have proposed experiments to detect potential pixelation or computational artifacts in space-time, which, if found, might hint at a simulated nature. The hypothesis also raises ethical and existential questions. If we are simulations, what is the moral responsibility of the creators or operators? Are we part of a grand experiment, entertainment, or something else entirely? This perspective can be unsettling but also inspiring, emphasizing the profound mystery of existence. In cultural and literary realms, the simulation idea has inspired numerous works, most famously the Matrix films, which explore the illusion of reality and the power of awareness and choice within a constructed world. In relation to the broader theme of reality's dependence on observation, the simulation hypothesis suggests that what we experience as real is contingent not only on being observed, but also on being processed by a conscious or programmed system. Observation inside the simulation may serve as the mechanism by which the universe's code produces consistent, stable realities. In summary, the simulation hypothesis insight offers a provocative lens on the nature of existence. It blends philosophy, quantum mechanics, and information theory to suggest that reality might be an intricate, observer-dependent digital construct. Whether true or not, this idea pushes us to question what it means to exist and who or what might be watching behind the scenes of our perceived universe. Among the many fascinating ideas about consciousness and reality, panpsychism stands out as an ancient yet increasingly discussed theory. It proposes that consciousness is not limited to humans or animals, but is a fundamental and ubiquitous feature of the universe. According to panpsychism, everything from particles and atoms to rocks and trees possesses some form of basic experience or awareness. This idea deeply intertwines perception and reality, suggesting that consciousness in its most elemental form is woven into the fabric of existence itself. Historically, panpsychism can be traced back to ancient philosophies, including certain strands of Greek thought and Eastern traditions, where the mind or soul was viewed as a pervasive aspect of nature. In contemporary philosophy and science, panpsychism is revisited to address the hard problem of consciousness, how subjective experience arises from physical processes. One compelling motivation for panpsychism is the difficulty in explaining consciousness purely as an emergent property of complex brain processes. If matter is entirely unconscious, how does the rich, subjective inner life emerge from mere physical interactions? Panpsychism offers a radical alternative. Consciousness doesn't emerge, but is a fundamental attribute of all matter. This implies that the universe is composed of countless tiny centers of experience, micro-consciousnesses, which combine or integrate to form the unified consciousness experienced by higher organisms. While the details remain debated, panpsychism suggests perception, awareness, or proto-consciousness is everywhere, embedded even at the quantum level. How does this relate to perception and reality? If consciousness is fundamental, then observation isn't just a feature of brains or minds, but a basic process existing throughout nature. Reality is, therefore, deeply tied to these pervasive perceptive processes. The act of observation or measurement, central to quantum mechanics, might be understood as interactions between fundamental conscious entities or proto-experiences. Some theorists propose that the observer effect and wave function collapse arise because even fundamental particles possess a form of perception, influencing quantum events. This view offers an elegant explanation for why observation matters so profoundly in physics, because perception itself is built into reality's foundation. Panpsychism also challenges the classic dichotomy between subject and object. Instead of a sharp divide between conscious observers and inert matter, the boundary blurs. The universe is a continuum of experience, from the simplest particle to the most complex mind. Philosophers like Alfred North Whitehead and David Chalmers have advanced versions of panpsychism that seek to integrate it with modern science. Whitehead's process philosophy views reality as a series of events or experiences, while Chalmers argues for fundamental experiential properties as part of nature's base. Critics often question how tiny conscious elements combine into unified consciousness, a problem called the combination problem, and worry that panpsychism risks being vague or untestable. Yet the theory remains appealing for those seeking to bridge the explanatory gap about mind and matter. Experimentally, panpsychism is difficult to verify directly, but it aligns intriguingly with quantum phenomena, where observer and observed seem inseparable. It also inspires new ways of thinking about the role of perception, suggesting that someone watching may not be restricted to human minds, but could be a universal feature. Philosophically, Panpsychism encourages humility and wonder, inviting us to see the world as alive with awareness at every scale. This worldview shifts our relationship with nature from detached spectatorship to participation in a vast network of conscious processes. In the context of the larger theme, theories that reality only exists if someone's watching, Panpsychism offers a unique perspective. It proposes that reality's existence depends on pervasive perception embedded in all things, making observation a universal, foundational aspect rather than a rare human event. In summary, Panpsychism and Perception challenge traditional materialistic views by suggesting that consciousness is fundamental and ubiquitous. This idea reshapes how we view reality, observation, and existence, highlighting the intimate connection between perception and the fabric of the universe. Awareness, often described as the subjective experience of perceiving and knowing, is a central yet elusive concept in understanding reality's relationship with observation. While physics examines how measurement influences quantum systems, it often leaves open the deeper question: what is the nature of awareness itself, and how does it contribute to the very existence of reality? Awareness differs from mere sensory input or passive reception. It is the active, conscious recognition of phenomena, the knowing that one knows. Philosophers and neuroscientists often distinguish between consciousness and awareness, with awareness sometimes viewed as the more fundamental, immediate experience. The idea that awareness plays a vital role in reality's unfolding finds roots in both ancient philosophical traditions and modern science. Many spiritual philosophies assert that awareness is the fundamental substrate of existence, underlying and giving rise to matter, energy, and even space-time. From a quantum perspective, awareness has been proposed as a key factor in the collapse of the wave function. The argument suggests that the indefinite probabilistic states of quantum systems crystallize into definite realities only when observed by an aware entity. Unlike an inanimate measuring device, a conscious observer with awareness selects outcomes, making awareness the bridge between possibility and actuality. This concept raises a host of intriguing questions. Is awareness a universal feature, as Panpsychism suggests, or is it unique to living beings with brains? Does awareness create reality, or is it an emergent property reflecting reality's structure? And if awareness is fundamental, what implications does that have for the nature of existence? Neuroscience explores awareness through studies of brain activity, attention, and self-reflection. While much progress has been made, awareness remains a hard problem. How subjective experience arises from neural processes is still deeply mysterious. The difficulty in explaining awareness resonates with the mysteries of quantum observation. Philosophers like David Chalmers have emphasized the explanatory gap between objective brain functions and subjective experience, arguing that awareness may require new fundamental principles beyond standard physical laws. This aligns with the idea that awareness might be essential to how the universe manifests itself. The role of awareness also intersects with interpretations of quantum mechanics that emphasize the observer. In such views, awareness does not merely passively record reality, but actively participates in shaping it. This elevates the observer from a peripheral figure to a co-creator of existence. Moreover, awareness introduces the concept of intentionality, the quality of being directed towards something which might influence how reality unfolds. Unlike blind measurement, awareness can reflect, choose, and even influence outcomes, raising fascinating possibilities about mind-matter interaction. In cosmology, some thinkers propose that awareness might have played a role in the universe's origins, suggesting that consciousness and reality are intertwined from the very beginning. This idea opens a vision of a universe evolving not only physically, but also consciously. However, these ideas are not without controversy. Critics caution against conflating physical measurement with conscious awareness, noting that many quantum processes occur without sentient observers. They argue that emphasizing awareness risks introducing anthropocentrism or metaphysical speculation beyond empirical science. Nevertheless, exploring the role of awareness invites us to bridge the gap between the objective and subjective, science and philosophy, matter and mind. It highlights the profound mystery that observation is not just about photons and particles, but about experience and knowing. In the context of theories that reality only exists, if someone's watching, awareness is the someone who watches, not just eyes or senses, but the conscious presence that makes observation meaningful. Without awareness, the notion of observation loses its essence. Reality may exist as a possibility, but remains unactualized. Ultimately, Understanding awareness's role challenges us to rethink the nature of existence, blending physics, philosophy, and consciousness studies. It beckons us toward a deeper grasp of how the universe and mind are entwined, revealing that the fabric of reality may be woven as much from awareness as from matter. The quantum Zeno paradox is a fascinating phenomenon in quantum mechanics that dramatically illustrates the power of observation, and in a sense, how watching can freeze reality itself. Named after the ancient Greek philosopher Zeno of Elea, famous for his paradoxes about motion and change, the quantum version demonstrates that a quantum system's evolution can be halted by frequent measurements, raising deep questions about observation and reality. At its core, the paradox shows that if a quantum system is observed repeatedly at very short intervals, the system's state can be frozen, preventing it from changing. In other words, continuous observation can inhibit the natural evolution or decay of a particle, effectively stopping time from the system's perspective. This is counterintuitive, because, classically, observation is passive. Looking at a clock doesn't stop its hands from moving, but quantum mechanics tells a different story. The state of a quantum particle is described by a wave function which evolves smoothly over time when unmeasured. However, each measurement collapses the wave function into a definite state, restarting the process. If measurements are made rapidly enough, the particle keeps collapsing back into the same state, preventing the system from evolving into a new state. This phenomenon was first theorized in the 1970s and later confirmed experimentally, demonstrating the strange interplay between measurement and dynamics. The quantum Zeno paradox reveals that observation is not merely passive, but actively influences the course of events at the quantum level. It embodies the principle that reality is not a fixed background, but a delicate process shaped by the act of measurement. Philosophically, this raises questions about the nature of time, change, and causality. If observation can halt evolution, what does this say about the flow of time? Is time itself dependent on interaction and observation? The paradox suggests that at the quantum level, temporal progression is intimately linked to measurement. The paradox also highlights how the observer's role can be surprisingly powerful, suggesting a universe where someone watching can control, or at least influence what happens. It challenges classical assumptions of an objective, observer-independent reality. The name Zeno references the ancient paradoxes, such as the arrow paradox, where motion is argued to be impossible because, at every instant, the arrow is at rest. The quantum Zeno effect similarly plays with the idea that frequent snapshots of a system prevent change. In practical terms, the quantum Zeno effect has implications for quantum computing and control, where manipulating the timing of measurements can preserve fragile quantum states and reduce decoherence. It suggests ways to stabilize quantum information by watching it carefully. The effect also appears in biological and chemical systems, influencing reaction rates and energy transfer processes, highlighting the wide reach of measurement's role beyond pure physics. Despite its counterintuitive nature, the quantum Zeno paradox underscores a profound truth that observation is not neutral but an active player in reality's unfolding. It exemplifies how the presence of an observer can shape not just what is known, but what is possible. In the broader context of theories that reality only exists, if someone's watching, the quantum Zeno paradox illustrates that continuous observation can literally sustain or freeze reality. It portrays the observer as a powerful force, whose attention can preserve the present and prevent change. This insight invites us to reflect on the intimate relationship between consciousness, measurement, and existence. It suggests that reality's very progression depends on the delicate dance of observation, collapse, and evolution, a dance choreographed by the watchers themselves. The concept of observer-created reality challenges the deeply ingrained notion that the world exists fully formed, independent of us. Instead, it posits that reality itself is in some fundamental sense brought into existence through the act of observation. This idea emerges from interpretations of quantum mechanics and philosophical reflections that emphasize the active role of the observer in shaping what is real. At the heart of this notion is the realization that quantum systems exist in a superposition of multiple possible states, and only through observation or measurement does one of these possibilities crystallize into actuality. This suggests that what we call reality is not a fixed backdrop, but a dynamic interplay between potentiality and observation. One striking example is the double-slit experiment, where particles like electrons display wave-like interference patterns when unobserved, but behave like particles passing through one slit or the other when measured. The mere act of observation changes the outcome, implying that observation helps create the phenomena observed. From this perspective, the observer is not just a passive receiver of information, but a co-creator of reality. The universe and the observer form a reciprocal relationship, where the observer's attention and measurement actively participate in determining the structure and behavior of physical systems. Philosophically, this idea aligns with strands of idealism and constructivism, which argue that reality is fundamentally dependent on mind or cognition. It also resonates with participatory universe concepts, which view observation as essential to the universe's very existence. However, observer-created reality does not necessarily require a conscious mind in the traditional sense. Some interpretations emphasize that any interaction that extracts information, whether by a human, a detector, or even a natural system, counts as observation, collapsing possibilities into a definite outcome. Thus, reality is created through interaction and information exchange. The observer-created reality framework raises intriguing questions about the nature of existence before observation. Was the universe unreal before conscious beings appeared? Or does a broader definition of observation, including environmental interactions, ensure that reality remains consistent? Some scientists suggest that the environment continuously measures quantum systems, effectively collapsing wave functions constantly and creating an objective classical world. Others propose that consciousness holds a unique role, giving rise to subjective realities that shape the world at a more profound level. The idea also has parallels in modern psychology and social science, where perception, attention, and belief influence not only personal experience but social reality. This interplay between mind and world highlights that reality may be more fluid and dependent on interaction than classical physics suggests. In practical terms, observer-created reality informs interpretations of quantum computing, quantum cryptography, and information theory, where the outcome of quantum processes depends on measurements made by observers. It underscores the significance of the observer in harnessing and controlling quantum phenomena. Yet, this concept invites profound philosophical and existential reflection. If reality depends on observation, what does that mean for objective truth? Is reality fragmented into many observer-dependent worlds? Can multiple realities coexist, each created by different observers? These questions have inspired debates about the nature of truth, consciousness, and the universe itself. They challenge reductionist views that exclude the observer from the picture, urging a holistic understanding where mind and matter are inseparable. In the context of theories that reality only exists if someone's watching, observer-created reality stands as a central pillar. It asserts that observation is not merely a window onto a pre-existing world, but the process through which the world takes shape. This view elevates the observer from passive spectator to active participant, highlighting the intimate connection between awareness and existence. It suggests that reality, far from being fixed and immutable, is a living, evolving tapestry woven through countless acts of observation. In conclusion, the idea of observer-created reality challenges us to rethink our relationship with the world. It suggests that what we see, measure, and know is not merely out there, but is brought forth through our engagement with it. Reality, in this light, is as much a product of the observer's act of watching as it is of the material universe itself. The reality we experience every day is far from a direct mirror of the external world. Instead, it is a constructed experience, filtered and shaped by our brains. The concept of the brain's reality filter explores how our nervous system selects, processes, and interprets sensory information to create a coherent, stable picture of reality, one that may be only a partial or even misleading representation of the true nature of existence. Our senses receive an overwhelming flood of stimuli, light, sound, pressure, chemicals, but the brain cannot process all of it simultaneously. Instead, it filters out much of this input, focusing on what is relevant for survival and coherence. This filtering shapes not only what we perceive, but also what we consider real. Neurological processes organize raw sensory data into meaningful patterns. The brain fills in gaps, predicts outcomes, and suppresses contradictory information, often prioritizing consistency and utility over accuracy. Optical illusions and cognitive biases are reminders that perception is an active, constructive process, not passive reception. The brain's filtering system extends beyond sensory data. Our expectations, beliefs, memories, and emotions profoundly influence what we notice and how we interpret it. This subjective lens means reality is, to a significant extent, co-created by the mind. From the perspective of quantum mechanics and observer theories, the brain's role becomes even more intriguing. If reality depends on observation and measurement, then the brain, as the ultimate observer, plays a crucial role in determining the experienced world. The brain's reality filter can be seen as the interface where quantum potentials collapse into the experienced actualities. This interplay raises important questions. Does the brain merely observe an independent reality, or does it participate in creating it? How much of what we call reality is shaped by neural processing rather than the external world? Such questions challenge classical objectivity and invite a more nuanced understanding of perception. Research in neuroscience has revealed remarkable brain mechanisms that influence reality perception. For example, the brain integrates signals over time and space to create a seamless experience of continuity, despite the discrete and noisy nature of sensory inputs. It employs predictive coding, constantly anticipating and updating its model of the world. Moreover, the brain can alter perception dramatically in altered states, such as dreams, hallucinations, or meditative absorption, showing that reality is malleable and dependent on brain state. These states illustrate that our experience is not a fixed reflection, but a dynamic construction. Philosophers of mind have long argued that consciousness and perception are fundamental to how reality is known and understood. The brain's filtering is part of this process, shaping not only what is observed, but also the very concept of existence. The brain's reality filter also has profound psychological and existential implications. It suggests that our sense of a stable, continuous world is an achievement of cognitive processing, and that beneath this stability lies a deeper, more uncertain realm. This aligns with themes in quantum mechanics where unobserved systems exist in superpositions of possibilities. Our brain's filtering might be the mechanism by which these possibilities are rendered into definite experiences, bridging the quantum and classical worlds. In practical terms, understanding the brain's role in shaping reality informs fields like virtual reality, where artificial inputs can convincingly alter perception, and psychology, where cognitive distortions affect well-being. The concept also urges humility in our claims about objective reality. If our brains filter and shape what we see, hear, and feel, then all knowledge is mediated and partial, reminding us that reality as we know it is a collaborative creation between the world and our minds. In the larger theme of theories that reality only exists, if someone's watching, the brain's reality filter exemplifies the someone watching. It is the complex biological observer that interprets, selects, and actualizes potential realities into lived experience. In conclusion, the brain's reality filter is a crucial component of how observation shapes existence. It transforms raw data into meaningful experience, enabling consciousness to witness and participate in the unfolding of reality. This insight deepens the understanding that reality depends not only on being observed, but on the active interpretative observer at the heart of perception. Quantum entanglement is one of the most mysterious and fascinating phenomena in physics. It occurs when two or more particles become linked, so that the state of one instantly influences the state of the other, no matter how far apart they are. This connection defies classical notions of locality and causality, and has profound implications for our understanding of observation and reality. The essence of entanglement is that the properties of entangled particles cannot be described independently. Instead, their states are correlated such that measuring one immediately determines the state of the other. For example, if two entangled electrons have spins that must be opposite, measuring one's spin as up instantly reveals the other's spin as down, even if they are light years apart. What makes entanglement particularly striking is that the measurement of one particle seems to instantaneously affect the other, suggesting a kind of non-local connection that challenges classical ideas of space and time. This phenomenon puzzled even Einstein, who famously called it spooky action at a distance, doubting that nature could allow such instantaneous effects. Entanglement reveals that observation plays a critical role in shaping reality. Until measurement, entangled particles exist in a combined superposition of states. Measurement on one collapses the entire system's wave function, defining the outcomes for both particles simultaneously. This process underscores the idea that observation is not passive, but actively determines the state of reality. The role of observation in entanglement deepens the theme that reality exists because it is being watched. Entangled particles exhibit correlations that only manifest when measurements are performed. Without observation, their combined state remains indefinite, described by probabilities rather than fixed values. Experiments confirming entanglement have been conducted extensively, including Bell test experiments, which demonstrate that no local hidden variables can explain the observed correlations. These results firmly establish entanglement as a real, fundamental feature of quantum mechanics. The implications of entanglement extend beyond physics. They challenge the classical idea that objects have independent intrinsic properties, suggesting instead that relationships and context are fundamental. This relational aspect resonates with interpretations like relational quantum mechanics, where states are observer-dependent and context-specific. Entanglement also inspires technological innovations. Quantum computing harnesses entanglement to perform computations far beyond classical capabilities. Quantum cryptography uses entanglement's properties to create unbreakable communication channels, emphasizing how observation and entanglement can be practically harnessed. Philosophically, entanglement prompts us to rethink the fabric of reality. If parts of the universe are deeply connected regardless of distance, the notion of separate, isolated entities may be an illusion. Instead, reality might be a holistic, interconnected web where observation and relationship define existence. This interconnectedness suggests that someone watching is not merely an individual isolated observer, but a participant in a vast network of relationships. Observations affect not only local outcomes but also distant entangled partners, weaving a reality shaped by collective interaction. In summary, entanglement and observation together illustrate that reality's nature transcends classical separability. Observation plays a fundamental role in defining the states of entangled systems, emphasizing that reality depends on being observed, measured, and related. This deep connection between observation and entanglement continues to reshape our understanding of the quantum world and the role of the observer. The holographic principle is a revolutionary idea in theoretical physics, suggesting that our three-dimensional reality might be a kind of projection from information encoded on a two-dimensional boundary, much like a hologram. This concept challenges traditional notions of space, reality, and observation, providing a fresh lens on how the universe and reality itself might be constructed. The principle originated from studies of black holes and quantum gravity. Physicists discovered that the information contained within a black hole, traditionally thought to reside throughout its volume, actually scales with the surface area of its event horizon, not the volume inside. This surprising insight led to the conjecture that the entire universe could be described similarly. All the information defining our three-dimensional world might be encoded on a distant two-dimensional boundary. In this framework, the universe's physics operates like a hologram, where the three-dimensional reality emerges from the encoding on a lower-dimensional surface. This perspective aligns intriguingly with quantum mechanics and information theory, highlighting the deep connection between information, space, and reality. The holographic principle also reframes the role of observation. If the universe is a hologram, then what we perceive as reality depends on decoding or reading the information stored on this boundary. Observation thus becomes an act of extracting or interacting with encoded information, linking measurement directly to the fabric of reality. This idea resonates with the broader theme that reality only exists if observed. The holographic universe suggests that what we call space and matter are emergent phenomena from informational content, which itself is realized through interactions and observation. The principle has been formalized in string theory, particularly through the AD/CFT correspondence, which mathematically relates a gravity theory in a higher dimensional space to a quantum field theory on its lower dimensional boundary. This duality provides a powerful framework to understand black holes, quantum gravity, and the emergence of spacetime. Philosophically, the holographic principle challenges the classical view of reality as a fixed, three-dimensional space filled with objects. Instead, it presents a universe where space and matter emerge from a more fundamental informational substrate, dependent on how and whether that information is accessed or observed. This insight has profound implications for understanding the observer's role. It suggests that observation is not just about measuring existing properties, but participating in the decoding process that brings reality into existence. In other words, observers are integral to the universe's holographic fabric. Experimentally, aspects of the holographic principle remain theoretical, though physicists are exploring ways to detect holographic noise or signatures in the cosmic microwave background and gravitational wave observations. These efforts seek to uncover whether the universe truly exhibits holographic properties. In technology, the principle inspires quantum information science and advances in quantum computing, where encoding, decoding, and processing information in novel ways echoes the holographic universe's underlying structure. The holographic principle also intertwines with other theories, emphasizing information's primacy, reinforcing the idea that reality is fundamentally about bits, measurements, and observations, rather than tangible particles alone. In summary, the holographic principle offers a radical reimagining of reality, where the three-dimensional universe emerges from two-dimensional information encoded on a cosmic boundary. Observation is the process through which this information is accessed, decoded, and transformed into the experienced world. This perspective deepens the theme that reality depends on observation, highlighting the central role of the observer in manifesting existence itself. Quantum Bayesianism, often referred to as cubism, is a modern interpretation of quantum mechanics that reimagines the role of probability, measurement, and the observer's knowledge. Drawing inspiration from Bayesian probability theory, a framework that updates beliefs based on new evidence, cubism treats the wave function and quantum states not as objective realities, but as expressions of an observer's personal degrees of belief about a system. At its core, cubism emphasizes that quantum probabilities are subjective. They reflect an individual agent's uncertainty and expectations rather than inherent properties of the physical world. When an observer makes a measurement, they update their beliefs about the system accordingly, akin to how one updates a weather forecast after receiving new data. This perspective shifts the interpretation of quantum mechanics from describing external reality to describing an observer's information about reality. The wave function becomes a tool for managing and updating expectations rather than a physical entity. This approach elegantly sidesteps many conceptual problems, such as wave function collapse and the measurement problem, by reframing measurement as a personal update of beliefs. Cubism also insists on the centrality of the observer, not as a detached recorder, but as an active participant who assigns meaning to measurements and outcomes. The theory posits that quantum mechanics is a guide for agents making decisions and predictions based on their experiences, highlighting the inseparability of observer and observed. The theory's roots lie in the Bayesian interpretation of probability, which contrasts with frequentist views treating probability as objective long-run frequencies. Bayesianism is inherently subjective, focusing on how agents revise their degrees of belief as new information arrives. Cubism extends this to quantum events, framing them as personal experiences that shape knowledge. One of cubism's strengths is its ability to reconcile quantum mechanics with a realistic worldview, while avoiding paradoxes arising from objective wave functions. By treating quantum states as epistemic rather than ontic, it removes the mystery of wave function collapse, replacing it with Bayesian belief revision. Cubism also offers insights into the role of measurement. Measurement outcomes are not predetermined properties, but personal experiences elicited by the interaction between agent and system. Thus, reality is co-created through these interactions, resonating with participatory universe ideas. Critics argue that cubism risks solipsism or radical subjectivism, questioning whether it can account for the objective consistency of the physical world. However, cubists emphasize that while quantum states are subjective, the external world exists independently and constrains agents' experiences, maintaining an objective underpinning. Philosophically, cubism aligns with pragmatic and instrumentalist traditions, focusing on the usefulness of theories to guide action and prediction, rather than making metaphysical claims. It highlights that science is an ongoing dialogue between agents and nature, centered on information exchange. In relation to the broader theme, that reality only exists if observed, cubism places observation and personal experience at the heart of existence. Reality in cubism is not a fixed structure out there, but a continually evolving tapestry shaped by agents' interactions and updated beliefs. This approach has practical implications for quantum information science and quantum computing, where managing and updating knowledge about quantum states is crucial. Cubism informs protocols for quantum communication, cryptography, and error correction. In summary, Quantum Bayesianism offers a fresh, subjective interpretation of quantum mechanics, emphasizing the observer's role as an active participant, updating beliefs through measurement. It reframes reality as a personal, experiential construct, intertwined with observation, deepening our understanding of how and why reality depends on someone watching. One of the most intriguing ideas emerging from modern physics and philosophy is the notion of a reality dependence loop, a circular relationship where reality depends on observation, and observation in turn depends on reality. This loop challenges traditional linear cause and effect thinking, and suggests that existence and observation co-create each other in a self-referential cycle. At the heart of this concept is the idea that reality isn't a fixed observer-independent stage, but but a dynamic participatory process. Quantum mechanics reveals that the state of a system often remains indeterminate until measured, but this measurement depends on the existence of observers capable of interaction and awareness. Thus, reality requires observers to bring it into being, yet observers themselves arise within that reality. This mutual dependency forms a feedback loop. Reality shapes observers, who then shape reality through observation. It's a profound circularity that echoes philosophical notions like the participatory universe and observer-created reality, highlighting the inseparability of existence and consciousness. The dependence loop can be viewed through the lens of quantum measurement. Before observation, quantum systems exist in superpositions of possibilities. The act of measurement, performed by an observer or a measuring device, collapses these possibilities into a definite state, creating concrete reality. But measurement outcomes depend on the experimental setup, the observer's choices, and the context, meaning observation doesn't just reveal reality, it partly constructs it. This leads to a puzzle. If observers are needed to collapse wave functions and produce reality, how did the universe exist before conscious beings appeared? Some suggest that simpler forms of proto-consciousness or environmental interactions suffice to instantiate reality, while others propose that the loop is timeless and self-sustaining. Philosophically, the dependence loop aligns with ideas of co-emergence and reflexivity, where entities arise together through mutual influence. It challenges the classical separation of subject and object, observer and observed, emphasizing relational existence. This looping concept also touches on ideas from Eastern philosophies, which often stress interdependence and the co-arising of phenomena. Reality in this view is not a static backdrop, but a flowing, interwoven dance of awareness and manifestation. Practically, the dependence loop informs quantum information theory, where information exchange between systems is fundamental. Observation is not a passive snapshot, but an interactive dialogue that generates reality's structure. The loop challenges the notion of absolute objective reality, suggesting instead that what is real is contingent upon observers embedded within the universe. It implies that the universe is incomplete without participation, making observation a creative act that continually brings reality forth. This idea also resonates with contemporary cognitive science, where perception and consciousness are seen as active, constructive processes rather than passive receptions. Our brains don't just record reality, they co-create it through interpretation and attention. In conclusion, reality's dependence loop is a profound insight into the intertwined nature of existence and observation. It reveals a cosmos where reality and observers emerge together, each shaping and sustaining the other. This circular dance defies simple causality and invites us to see existence as a participatory relational process, where being and watching are inseparable. In quantum mechanics, one of the most puzzling and debated phenomena is the collapse of the wave function, the moment when a quantum system's multiple possible states reduce to a single, definite outcome. The idea that this collapse occurs specifically because of observation raises profound questions about the nature of reality and the role of the observer. The wave function is a mathematical representation that encodes all possible states of a quantum system simultaneously, a superposition. Before measurement, a particle like an electron can be in multiple positions or spin states at once. Upon observation or measurement, this superposition appears to collapse, leaving the particle in just one of these states. But what exactly causes this collapse? One interpretation suggests that observation itself is the trigger. This view holds that the act of observing, a measurement by a conscious or physical system, forces the system to choose a definite state. Without observation, the system remains in an indefinite probabilistic condition. This idea raises deep conceptual challenges. If observation collapses the wave function, then reality itself depends on being observed. This view links closely to thought experiments such as Schrödinger's cat, where the cat inside the box is simultaneously alive and dead. Until someone looks, the observer's presence is critical to the system's definite state. Physicists debate whether collapse requires a conscious observer, or if interaction with any measuring apparatus suffices. Some argue that the collapse results from physical interaction. When a quantum system couples with a macroscopic device, decoherence causes effective collapse without consciousness. Others maintain consciousness plays a fundamental role, making the observer uniquely significant. The notion of collapse by observation challenges classical realism, which posits that physical properties exist independently of observation. Quantum mechanics through collapse suggests that some aspects of reality are indeterminate until measured, implying reality is not fully formed without observation. Experiments have demonstrated that different measurement choices affect outcomes, reinforcing the idea that observation plays a causal role. In delayed choice experiments, for example, whether or not a measurement is made can retroactively influence earlier behavior of quantum particles, highlighting the mysterious timing of collapse. The collapse process also raises questions about the nature of time and causality. Does collapse happen instantaneously? Does it depend on the observer's frame of reference? These questions remain unresolved, fueling ongoing research and debate. Collapse by observation has practical implications. Quantum technologies, such as quantum cryptography and computing, rely on precise control of measurement and collapse. Understanding how and when collapse occurs is essential to harnessing quantum systems. Philosophically, this concept blurs the line between observer and reality. The observer is not just a passive witness, but an active participant whose presence and actions help define the universe's state. This participatory view transforms our understanding of existence and knowledge. However, collapse by observation also invites skepticism. Critics question whether collapse is a physical event or just a change in information available to the observer. The many worlds interpretation denies collapse, suggesting that all outcomes occur but observers become entangled with particular branches, removing the need for a special collapse event. Despite controversies, collapse by observation remains a central feature of quantum theory and a focal point for exploring how observation shapes reality. It embodies the core mystery that reality only crystallizes when looked at, reinforcing the idea that someone watching is crucial for existence. In conclusion, collapse by observation highlights the profound influence of observation on reality's formation. It challenges traditional ideas about independent, objective reality, suggesting instead that reality emerges through the active role of observation. This idea deepens our understanding of the quantum world and the intertwined nature of observer and observed. The question of whether reality exists independently of observation has long captivated philosophers, physicists, and thinkers alike. Reality without witness explores the notion of a world that continues unabated, even when no conscious observer is present, a concept that challenges interpretations, suggesting reality depends fundamentally on being watched. Classically, most people assume an objective reality. Mountains stand tall whether or not anyone is there to see them. Stars shine in distant galaxies, irrespective of observation. This intuitive view holds that the universe exists independently of us, waiting to be discovered but not contingent on our awareness. However, quantum mechanics complicates this picture. At the subatomic level, particles seem to exist in indefinite states, superpositions, until measured or observed. This has led some interpretations to propose that the universe's fabric depends on observation, raising the question, what happens to unobserved reality? Does it vanish, exist only in potential, or follow other rules? Some physicists argue that reality without witness is sustained through processes independent of conscious observers. The environment, with its countless particles and fields, acts as a ubiquitous observer, constantly interacting and measuring systems through decoherence. This means that even in the absence of humans or conscious beings, physical interactions suffice to maintain an objective reality. This approach aligns with the decoherence theory, which explains why macroscopic objects do not exhibit quantum superpositions. They continuously interact with their surroundings, causing wave function collapse-like effects without requiring conscious observation. Reality in this view is robust and stable, persisting regardless of human awareness. Yet, this perspective raises deep philosophical questions about what counts as observation. Is a photon interacting with another particle observing in the meaningful sense? Does this interaction generate reality, or is conscious awareness essential for actualizing the universe? The idea of reality without witness also touches on cosmology. Before life emerged on Earth, billions of years passed. Did the universe exist in a definite state during this time, or was reality somehow incomplete or potential, until observers arose? Most scientists believe the universe existed objectively, supported by physical laws independent of observation. Philosophically, this debate pits realism, the belief in an observer-independent world, against idealism or participatory universe ideas. The former posits a universe that exists out there, regardless of observation, while the latter sees reality as co-created through awareness and measurement. Some interpretations, like the many worlds theory, maintain that all possible realities exist simultaneously, independent of observation, with the observer becoming entangled within one branch. This preserves reality without requiring collapse or a witness to actualize outcomes. Others propose that reality without witness exists as a cloud of probabilities or potentialities, an indeterminate realm, until observed, suggesting a universe that is partially incomplete or undefined without interaction. The question also reverberates in existential and metaphysical domains. If reality depends on observation, what does that say about the nature of existence? Can something be said to exist if entirely unperceived? And if reality persists without witnesses, what role does consciousness truly play? In practical terms, this inquiry informs interpretations of quantum mechanics, cosmology, and the philosophy of science. It impacts how we understand objectivity, measurement, and the limits of knowledge. Moreover, it invites us to reflect on our place in the cosmos. Whether reality requires observation or not, human awareness imbues existence with meaning and perspective, shaping how we relate to the universe. In conclusion, reality without witness presents a fundamental challenge to theories that reality exists only if observed. It affirms the possibility, and for many, the necessity of an objective world independent of consciousness. Yet, quantum phenomena continually remind us that observation plays a critical role in how reality manifests. This tension remains at the heart of modern physics and philosophy, inviting ongoing exploration of the delicate balance between existence and awareness. One of the most striking and counterintuitive features of quantum mechanics is that measurement does not merely reveal reality, but actively changes it. Unlike classical physics, where measurement is assumed to be a passive act that observes pre-existing properties, quantum measurement induces fundamental changes in the system being observed. This phenomenon is known as measurement-induced change, and it reshapes our understanding of the observer's role in reality. In classical physics, measuring a property like position or velocity is considered a straightforward reading. The object has a definite state, and the measuring device simply uncovers it. However, in the quantum world, particles exist in superpositions, multiple possible states simultaneously, and measurement forces the system to choose one outcome. This process, often called wave function collapse, means that before measurement, a particle's properties are not definite, but probabilistic. The act of measurement reduces this uncertainty, changing the system's state in an irreversible way. In essence, the observer's action alters the system, collapsing potentiality into actuality. A famous example is the double-slit experiment. When electrons pass through two slits unobserved, they form an interference pattern characteristic of waves, indicating they traverse both slits simultaneously. But if a measurement device determines which slit the electron goes through, the interference disappears, and the electron behaves like a particle. The measurement changes the behavior and reality of the electron. This measurement-induced change challenges the traditional notion that the world is independent of observation. Instead, it suggests that the observer plays an active role in shaping what happens, creating reality through interaction. The nature of this change is subtle and complex. Measurement involves an interaction between the quantum system and the measuring apparatus, leading to entanglement and decoherence. This process spreads quantum information into the environment, making superpositions unobservable at macroscopic scales and giving rise to classical reality. However, the exact mechanism and interpretation of measurement-induced change remain debated. Does measurement physically alter the system, or is it a change in our knowledge? The Copenhagen interpretation treats collapse as a physical process triggered by measurement, while other views, like many worlds, deny collapse and interpret measurement as branching into multiple outcomes. Measurement-induced change also plays a crucial role in quantum technologies. Quantum computers rely on precise measurements to extract information without destroying delicate quantum states prematurely. Understanding and controlling measurement is essential for advancing quantum communication, cryptography, and sensing. Philosophically, this phenomenon blurs the line between observer and observed, subject and object. The world is not a fixed backdrop, but a dynamic process continually shaped by observation and interaction. Reality emerges through countless measurement-induced changes across scales. This perspective has profound implications for the nature of knowledge and existence. If reality changes through observation, what does this mean for objective truth? Is reality observer-dependent and fluid, or is there a deeper level of permanence beneath the apparent changes? Measurement-induced change also invites reflection on the nature of causality and time. If observation alters outcomes, the causal sequence can appear non-classical, as in delayed choice experiments, where future measurements affect past behavior. In sum, measurement-induced change underscores the active, creative role of observation in quantum mechanics. It reveals a universe where someone watching is not passive but a catalyst for reality's ongoing formation. This insight challenges classical assumptions and deepens our understanding of existence's participatory nature. The notion that consciousness itself acts as an observer in quantum mechanics is a captivating and often controversial idea that has profound implications for how we understand reality. Unlike classical views that treat observers as passive, detached entities, this perspective suggests that conscious awareness plays an active and essential role in shaping the physical world. Quantum theory reveals that systems exist in multiple states simultaneously, a superposition, until measured. The act of measurement collapses this superposition into a single, definite state. But what constitutes a measurement? Some interpretations propose that only a conscious observer's awareness can trigger this collapse, elevating consciousness from a mere spectator to a fundamental participant in reality's formation. This view traces back to early quantum pioneers like Eugene Wigner, who argued that consciousness is necessary to cause wave function collapse. If true, this means that physical reality is intimately linked to conscious experience, and that the universe depends on observers not just to know it, but to bring it into being. Philosophically, consciousness as observer resonates with idealism, which posits that mind or awareness is primary, and matter emerges from it. It also connects with certain mystical traditions that view consciousness as the fundamental ground of existence. Yet, the consciousness-centric interpretation raises many questions and challenges. How does consciousness interact with quantum systems to cause collapse? Does this imply that inanimate objects or measuring devices cannot collapse wave functions without conscious involvement? What defines consciousness in this context? Moreover, this view confronts the problem of solipsism, the idea that only one's own mind is certain to exist, and challenges how to account for shared objective reality if collapse depends on individual consciousness. Critics argue that quantum collapse occurs in many situations without conscious observers, such as interactions between particles or measuring devices, and that attributing collapse solely to consciousness risks blurring science with metaphysics. Nonetheless, some modern theories propose mechanisms linking consciousness and quantum processes in the brain. The orchestrated objective reduction, OR theory, by Roger Penrose and Stuart Hameroff, suggests that microtubules in neurons harness quantum coherence, connecting consciousness and quantum collapse. This perspective fuels ongoing debates in neuroscience, physics, and philosophy, probing whether consciousness is fundamental to nature or an emergent phenomenon, explainable by classical physics. Practically, the consciousness as observer idea inspires interdisciplinary research, aiming to bridge subjective experience with objective science. It motivates investigations into quantum effects in biology and consciousness studies. In relation to the broader theme that reality only exists if someone's watching, this interpretation emphasizes that someone is not just any measuring device but conscious awareness itself. Without consciousness, reality may remain indefinite, a cloud of possibilities awaiting actualization. This elevates consciousness to a cosmic role, suggesting that our minds are essential components in the fabric of reality, shaping existence through observation and awareness. In summary, consciousness as observer challenges materialistic assumptions, proposing that awareness is a fundamental actor in quantum measurement and reality's manifestation. It bridges physics and philosophy, inviting us to reconsider the profound relationship between mind and matter and the mysterious power of observation. The many-worlds interpretation, MWI, of quantum mechanics, presents a radical and fascinating perspective on reality and observation, positing that every possible outcome of a quantum measurement actually occurs, but in separate, branching universes. In this framework, the observer is not witnessing a collapse to a single outcome, but becomes entangled with a multitude of parallel versions of reality, each as real as the next. MWI was first proposed by physicist Hugh Everett in 1957 as a solution to the measurement problem and the paradoxes arising from wave function collapse. Instead of assuming that measurement causes the wave function to suddenly reduce to a single outcome, Everett suggested that all outcomes coexist simultaneously in a vast multiverse. The wave function never collapses, it simply evolves unitarily, encompassing every possibility. In this picture, the role of the observer transforms dramatically. When an observer measures a quantum system, their own state becomes entangled with the system's possible outcomes. This means the observer splits into multiple versions, each perceiving a different outcome. Each branch forms a distinct, non-communicating world where a unique measurement result is realized. This interpretation preserves the deterministic evolution of quantum mechanics while explaining why observers experience definite outcomes. From the perspective of any single branch, the measurement looks like a collapse, but globally the entire wave function remains intact, containing all possible histories. The observer in many worlds is both a participant and a witness to this branching reality. Their experience is localized to a single branch, but the full quantum state includes all branches simultaneously. This eliminates the special role of consciousness in causing collapse, instead attributing the appearance of collapse to the observer's subjective experience within one branch. Philosophically, MWI raises profound questions about identity and reality. If countless versions of you exist across branches, each experiencing different outcomes, what does that mean for individuality, free will, and personal identity? Are these parallel observers truly distinct, or aspects of a larger whole? The multiverse also challenges classical notions of a unique, objective reality. Instead, reality is a vast, branching tree of possibilities, continuously splitting as measurements occur. This vastness reconciles the probabilistic nature of quantum outcomes with deterministic physical laws. Experimentally, MWI makes the same predictions as standard quantum mechanics, making it difficult to test directly. However, its conceptual clarity and mathematical consistency attract many physicists and philosophers. The observer's role in many worlds emphasizes that reality is not singular, but richly plural. Each observer experiences a definite world, but the global picture is a tapestry of countless intertwined realities. This interpretation aligns intriguingly with ideas in cosmology and theoretical physics, suggesting a multiverse on a grander scale, where many universes with varying physical laws may exist. In relation to the theme that reality only exists if someone's watching, MWI suggests that every possible observation is realized by some observer somewhere, but each observer is confined to their own branch. Observation is a branching process rather than a collapsing event. This perspective offers a compelling way to reconcile the weirdness of quantum mechanics with a consistent ontology, preserving both reality's richness and the observer's experience. In summary, the observer in many worlds presents a universe of infinite branching realities, where observers play a central role by splitting into multiple versions corresponding to every possible outcome. It challenges classical notions of collapse and uniqueness, portraying reality as a complex, observer-dependent multiverse continuously created by observation itself. The observer in quantum mechanics occupies a profoundly paradoxical position, both central and elusive, active yet passive, crucial yet mysterious. This observer's paradoxical role lies at the heart of quantum theory's conceptual challenges, revealing deep tensions about what it means to observe and to be observed, and how observation shapes reality itself. On one hand, the observer appears indispensable. Quantum experiments show that the act of measurement or observation changes the state of the system. Without observation, particles exist in superpositions. With observation, these superpositions collapse into definite outcomes. This makes the observer a fundamental participant, without whom reality remains indefinite. On the other hand, the observer must also be part of the physical universe, subject to the same laws. How can the observer be both inside and outside the system? If the observer is also a quantum system, how does measurement and collapse occur? This creates a loop of self-reference, where observers observe as leading to ambiguities and paradoxes, such as those highlighted by the Wigner's friend thought experiment. The paradox extends further. The observer is required to define reality, yet their own state depends on that reality. This circularity challenges classical ideas of objective, observer-independent existence, and invites new ways of thinking about reality as relational and participatory. Moreover, the observer's paradox touches on consciousness and awareness. If consciousness is necessary for collapse, then what about unconscious observers or automated measuring devices? If observation is any physical interaction, extracting information, does the observer's paradox diminish? These questions remain unresolved, fueling diverse interpretations. Philosophically, the observer's paradox illustrates the blurred line between subject and object, mind and matter. Observation is not a detached act, but an entangled process, where the observer and observed co-create reality. This challenges Cartesian dualism and invites holistic perspectives. The paradoxical role also has implications for knowledge and epistemology. If reality depends on observation, then what can be said to exist independently of observation? Can knowledge ever be absolute, or is it always conditioned by the observer's perspective and interaction? In scientific practice, the observer paradox requires careful consideration in experimental design and interpretation. Understanding how measurement influences outcomes is crucial in quantum information science, quantum computing, and foundational physics. Interpretations like relational quantum mechanics address the paradox by proposing that states are relative to observers. No absolute state exists independent of observation. Many worlds sidestep collapse by embracing all outcomes, while cubism treats quantum states as personal beliefs updated by observation. In everyday life, the observer's paradox can be seen metaphorically. Our perception shapes how we experience the world, and our actions, informed by observation, influence reality. This resonates with broader philosophical and spiritual traditions, emphasizing interdependence. In summary, the observer's paradoxical role is a profound feature of quantum mechanics and philosophy. It reveals a universe where observers are both creators and creations of reality, where observation is essential but enigmatic. This paradox challenges us to rethink existence, knowledge, and the very meaning of observation. Reality at the quantum level is far from static or deterministic. Instead, it is a fluid, dynamic process, a quantum dance of possibilities, interactions, and observations that continuously shape what is and what can be. This metaphor of a dance captures the intricate interplay between particles, waves, measurement, and consciousness, where nothing is fixed until the final step is taken by an observer. In classical physics, objects follow predictable paths, their states determined by initial conditions and natural laws. The universe is a well-rehearsed ballet, choreographed by gravity, electromagnetism, and other forces. Quantum mechanics, however, reveals a more improvisational performance, where uncertainty, superposition, and entanglement take center stage. At the heart of this dance is the quantum wave function, a complex choreography of all possible states a system can inhabit simultaneously, until an observation calls the steps. The system moves in a superposition, exploring different outcomes in parallel. Measurement acts like a spotlight, highlighting one path, and collapsing the wave function into a definite reality. This collapse is not a mere footnote, but an active transition where potentiality becomes actuality. Observation is thus an essential partner in the dance, transforming abstract probabilities into concrete phenomena. Reality emerges not as a fixed tableau but as a performance co-created by the system and the observer. Entanglement adds richness to this dance. When particles become entangled, their states are intertwined, their steps synchronized regardless of distance. Measuring one instantaneously influences the other, a non-local duet that defies classical separation. The dance is therefore not just local but a vast, interconnected web of relationships. Philosophers and physicists alike have been drawn to this metaphor to express the elegance and mystery of quantum behavior. It evokes a universe that is alive, responsive, and participatory, where existence unfolds through ongoing interaction. The quantum dance also challenges the notion of a singular, observer-independent reality. Instead, multiple potential realities coexist in the wave function's superposition, and the observer's measurement chooses one. This interplay introduces subjectivity and relationality, where different observers might witness different aspects of the dance. From a practical standpoint, this dance underlies the development of quantum technologies. Quantum computers rely on maintaining coherence in the dance of qubits, where superposition and entanglement enable parallel computation. Controlling the dance through careful observation and interaction is key to unlocking their power. The dance metaphor also illuminates the role of time and causality. Quantum events don't unfold in a strict linear sequence, but exhibit temporal flexibility, with delayed choice experiments showing that future measurements influence past behavior. Reality's dance is therefore not constrained by classical temporal order. Beyond physics, the quantum dance invites us to reconsider our relationship to existence. It suggests that reality is not a static background, but a dynamic, creative process in which observers participate actively. Our consciousness, attention, and observation are part of the choreography. In spiritual and philosophical traditions, this view resonates with concepts of flow, process, and co-creation, highlighting the interconnectedness of all things. Reality's quantum dance becomes a metaphor for the ongoing unfolding of being, where every moment is a new step in an eternal performance. In conclusion, reality's quantum dance offers a poetic and profound understanding of existence as a collaborative, fluid process shaped by observation, interaction, and relationship. It emphasizes that reality is not merely observed but actively brought forth through the dynamic interplay of quantum systems and conscious observers, embodying the very essence of the idea that reality exists only if someone is watching. The notion of mind-dependent existence challenges the classical assumption that the world exists fully and independently of our awareness. Instead, it proposes that existence, or at least the reality we experience, depends fundamentally on the mind's role as an observer, perceiver, and interpreter. This idea has deep roots in philosophy and finds intriguing resonance in quantum physics, where observation appears to shape the physical state of systems. Philosophically, mind-dependent existence draws from idealism, the view that reality is ultimately mental or experiential, rather than purely material. Classical idealists like Berkeley famously asserted that objects exist only as perceptions in minds. While this extreme form of idealism has been debated and refined over centuries, modern discussions explore subtler forms, suggesting that mind and reality are inseparable aspects of a unified whole. In quantum mechanics, the theme of mind-dependent existence gains new support. The measurement problem reveals that quantum systems remain in superpositions, multiple possible states, until an observation collapses this ambiguity into a definite outcome. Without an observer to measure, the system's state is indeterminate, suggesting that the very act of observation participates in bringing reality into concrete being. But does this observation require a conscious mind? Some interpretations hold that any interaction with a measuring device suffices, while others argue that consciousness itself is the unique factor that causes collapse. If consciousness is essential, then existence as we know it truly depends on mind. This view raises profound questions. Does the universe exist at all when unobserved? How does existence unfold in the absence of conscious beings? Some propose that mind-dependent existence implies a participatory universe, where reality and observers co-emerge and co-define each other in an ongoing dynamic process. The idea also ties into panpsychism, which suggests that mind or proto-consciousness permeates all matter, making mind dependence a fundamental feature of existence, rather than an anomaly confined to humans or animals. Philosophers and scientists continue to grapple with these implications. If existence depends on mind, then notions of objectivity, independent reality, and causality require re-examination. Reality might not be a fixed external arena, but a living interactive process involving observation and awareness. This perspective also aligns with findings in neuroscience and cognitive science, which show how perception and cognition shape our experience of reality. Our brain filters, interprets, and constructs the world we know, emphasizing the mind's central role in defining existence. In metaphysical terms, mind-dependent existence suggests that what we call existence is a relational property, arising only through the interplay between the world and conscious awareness. This view fosters humility about human knowledge, highlighting that our grasp of reality is mediated and incomplete. In the context of theories that reality only exists, if someone's watching, mind-dependent existence represents a profound affirmation of the observer's role. It insists that reality is not a passive stage, but an emergent phenomenon reliant on the mind's gaze. In conclusion, the concept of mind-dependent existence challenges us to rethink the foundations of reality. It invites a shift from materialism to a more integrated understanding, where mind and matter are entwined, perception and existence inseparable. This perspective deepens our appreciation of observation's power, revealing that what is may be inseparably linked to who observes. The role of the observer in collapse models of quantum mechanics presents a fascinating approach to resolving the measurement problem, by proposing that wave function collapse is a real physical process, triggered by specific mechanisms. These models challenge traditional views that collapse occurs mysteriously, or only upon conscious observation, instead offering objective, testable accounts of how quantum possibilities become definite realities. Collapse models, sometimes called dynamical reduction theories, posit that the wave function's evolution is generally governed by the Schrödinger equation, but occasionally undergoes spontaneous collapses, forcing a system into a definite state. Unlike interpretations where collapse is purely epistemic or observer-dependent, these models treat collapse as a physical phenomenon, independent of measurement or consciousness. One of the most prominent collapse models is the Ghirardi-Rimini-Weber (GRW) theory, which suggests that particles spontaneously localize at random intervals, with a tiny probability per unit time. While the chance of collapse for a single particle is low, the collective effect on macroscopic systems ensures classical definiteness emerges at larger scales. In collapse models, the observer is no longer the mysterious agent whose awareness triggers reality. Instead, collapse happens objectively and randomly, independent of any observer. The observer's role is thus passive. They discover the system's definite state after collapse rather than causing it. However, the observer remains essential in the process of gaining knowledge about the system. Measurements reveal which outcome the collapse has produced, and observers update their information accordingly. In this sense, observation is the interface through which collapse is accessed, but not the cause. This approach elegantly addresses key issues in quantum theory. It preserves the deterministic evolution of quantum systems most of the time, but adds a physical mechanism to explain how definite outcomes arise, avoiding paradoxes like Schrödinger's cat and Wigner's friend without requiring multiple worlds or subjective consciousness. Collapse models also make predictions that differ subtly from standard quantum mechanics, providing avenues for experimental testing. Researchers are actively investigating these differences to confirm or falsify collapse theories, pushing the boundaries of foundational physics. Philosophically, these models represent a middle ground between strict realism and observer-dependent views. They assert an objective reality with intrinsic randomness, where measurement reveals pre-existing collapse outcomes rather than creating them. Yet, questions remain about the nature of collapse triggers, their relation to gravity or other physical parameters, and how to integrate collapse with relativistic and field-theoretic frameworks. In relation to the theme theories that reality only exists, if someone's watching collapse models nuance the observer's role, they reject the idea that conscious observation is necessary to bring reality into existence, emphasizing that collapse occurs objectively. However, they acknowledge the observer's role in accessing and confirming reality's definite states. This perspective maintains the essential participatory relationship between observer and reality, but grounds reality's formation in physical processes rather than subjective awareness. It balances the demands of quantum theory, objectivity, and empirical testability. In summary, the observer in collapse models is a discoverer, not a creator, of reality. Collapse happens independently, and observation reveals the outcomes. This interpretation advances our understanding of measurement and reality's emergence, illustrating a world where observation is crucial but not the sole determinant of existence. The final piece in our exploration of theories about observation and reality is the concept of observer bias, the subtle yet powerful ways in which the observer's presence, expectations, and perceptions shape the reality they experience. While observer bias is often discussed in psychology and social sciences, its implications extend deep into physics, philosophy, and the fundamental nature of existence. At its simplest, observer bias refers to the tendency of observers to influence or interpret data in ways that confirm their preconceptions. In everyday life, this might mean seeing what we expect or desire, shaping our personal realities through perception and cognition. In quantum mechanics, observer bias takes on a more fundamental and intriguing dimension. The observer is not merely a passive recipient, but an active participant whose choices, measurement settings, and interpretative frameworks affect the outcome of experiments. The observer's expectations, knowledge, and even intentions can subtly influence the manifestation of reality. This idea connects with the participatory universe concept, where observation is a creative act, but observer bias highlights that this creativity is not neutral. It is filtered through the observer's subjective lens, introducing a form of bias that shapes reality's unfolding. The bias arises because observation in quantum physics is not a simple act of looking, but involves complex interactions between observer, apparatus, and system. The observer decides what to measure, how to measure, and which aspects of the system to highlight, thereby directing how reality collapses into one of many possibilities. Philosophically, observer bias challenges the notion of objective reality. If our observation is always filtered through subjective frameworks, then what we call reality is partly constructed by these biases. This aligns with ideas in constructivist epistemology, which hold that knowledge and reality are co-created by the observer and their context. In experimental science, recognizing and mitigating observer bias is crucial to obtaining reliable, reproducible results. Quantum experiments require careful design to minimize human influence, ensuring outcomes reflect nature's behavior rather than observer expectations. However, some interpretations of quantum mechanics embrace observer bias as an unavoidable and even necessary aspect of reality's formation. This perspective suggests that consciousness and observation shape reality in personalized ways, producing a world that is, to some extent, unique to each observer. The implications extend beyond physics. In psychology, sociology, and cognitive science, observer bias affects how humans understand themselves and their environment. influencing social reality, identity, and culture. These layers of bias intertwine with physical observation to create complex, layered realities. This interplay invites humility and self-awareness. Acknowledging observer bias reminds us that our grasp of reality is always partial, influenced by our perspectives, beliefs, and limitations. It encourages openness to alternative viewpoints and deeper inquiry. In the context of theories that reality only exists if someone's watching, reality's observer bias underscores that the someone is not a neutral witness, but a participant shaped by context, intention, and mind. Reality emerges through a dance between external phenomena and internal predispositions. In conclusion, reality's observer bias reveals the deeply participatory and subjective nature of existence. It challenges us to consider how observation shapes not only physical outcomes but the very fabric of reality through the lens of human perception. This final insight completes our journey into the profound and mysterious relationship between watching and being. As we reach the end of this profound journey through the intricate relationship between observation and reality, one theme emerges with remarkable clarity. Reality is not a fixed, independent stage waiting passively for discovery, but a dynamic, participatory phenomenon, fundamentally shaped by observation. From the quantum realm of superpositions and entanglement, to philosophical reflections on consciousness and mind-dependent existence, we have seen that someone watching is not a mere spectator, but a crucial agent in the unfolding of existence. Theories across physics, philosophy, and metaphysics converge to challenge the classical worldview of an objective, observer-independent universe. Instead, they paint a picture of a cosmos where the act of observing collapses possibilities into actuality, where conscious awareness may co-create reality, and where even space and time might emerge from informational and relational processes dependent on interaction. We explored how the observer effect reveals the power of measurement to influence particle behavior, transforming fuzzy potentials into definite outcomes. Schrödinger's cat paradox and Wigner's friend experiment highlighted the perplexing role of observers and the subjective nature of quantum facts. Concepts like the participatory universe and delayed choice experiments extended observation's influence beyond mere measurement, suggesting that present choices can shape past events, weaving time and existence into a complex tapestry of observer-dependent realities. The relational quantum mechanics interpretation reframed states as relative to specific observers, breaking from the notion of absolute reality, while the holographic principle introduced the radical idea that our three-dimensional universe might emerge from two-dimensional information, a projection made real by observation. Quantum Bayesianism emphasized the subjective nature of knowledge and belief in shaping reality, while the quantum Zeno paradox demonstrated how continuous observation can literally freeze evolution, showcasing observation's active role. Collapse models offered objective mechanisms for wave function collapse, balancing observer participation with physical realism. Philosophically, we reflected on panpsychism and mind-dependent existence, suggesting consciousness or proto-awareness may permeate all matter, making observation not just human-centric but universal. The brain's reality filter reminded us that our perception is itself a constructed experience, shaped by cognitive processes that turn raw data into meaningful reality. Throughout, the paradoxical role of the observer, simultaneously inside and outside the system, posed challenges to classical logic and causality, inviting us to accept a more relational, participatory, and fluid understanding of existence. The culmination of these ideas reveals a universe in constant quantum dance, where reality emerges through a delicate interplay between potentiality and observation, between mind and matter. Reality's dependence loop shows that observers and observed co-create each other in a self-referential cycle, emphasizing that existence and awareness are deeply intertwined. Yet, as we have seen with concepts like observer bias, reality is not merely shaped by observation but by the observer's context, beliefs, and intentions, highlighting the subjective dimension woven into the fabric of existence. What does this all mean for us? It suggests that our place in the universe is far more active and intimate than traditional views allow. We are not passive onlookers but participants whose awareness and choices contribute to the cosmos's unfolding. This perspective invites humility, responsibility, and wonder, recognizing that every observation is a creative act with profound significance. In essence, reality may be best understood, not as something out there independent of us, but as a living, evolving interplay between consciousness and the physical world. It challenges us to reconsider what existence means, to embrace the mystery of observation, and to appreciate that being watched and watching are two sides of the same cosmic coin. As you contemplate these ideas, let them inspire curiosity and reflection. The universe is far stranger and more beautiful than classical intuition allows, and you, as an observer, are part of this grand mystery. Reality only exists because someone is watching, and that someone is you.